Hi, everyone. I hope you can hear me. I'm Keith Hawkins. Can people hear me? I hope. All right, good. I'm Keith Hawkins. I am a professor at UT Austin, and I want to thank the organizers for giving me the opportunity to speak. I apologize I couldn't make it in person. I had a couple of family medical things that came up this week that was unexpected. Um, so much like Alex G and others in the early morning session, I'm a galactic archaeologist. I focus on individual stars in the Milky Way and stellar populations in the Milky Way. And so you might be thinking, at least I was when I got the invite to a cosmic dawn revealed by JWST conference, why me? Why, what is this? What is the relevance to this conference? And so I pulled up the conference website and I highlighted here some of the things that I thought were most relevant to some of my interests. Things like, what we can learn from JWST data on the nature of the first stars that piqued my interest in attending this particular conference, and the chemical enrichment histories of the early galaxies and early universe is also something that I'm particularly interested in as well. And so this talk will focus less so on galactic structure and dynamics, which is something I'm really excited about, to really focus on the topics that are much more related to this conference, kind of things related to the Milky Way and the local group as a laboratory for the role of accretion in galaxy assembly, and the Milky Way bulge, for example, as a local laboratory for the first stars, and local UFDs, or ultra-faint dwarf galaxies, and dwarf galaxies in general, as tracers of chemical enrichment histories of in the early universe and early galaxies. But of course, you should also see talks from this morning, Alex G, Rafaela, and others, as well as this afternoon, Stephania, who I may not be speaking, I guess, after all, Grace, Peter, and Jenna, as well as earlier talks from in the conference. I think that there were a lot of great talks, and I've been following along here in Texas. So I wanted to start with what I meant by the local group, or the Milky Way and the local group. So, this is essentially what I mean. This is the kind of a little cartoon showing the Milky Way and some of its local neighbors like Andromeda, all the way out to Andromeda, and all of the kind of dwarf galaxies and ultra faint dwarf galaxies and globular clusters and so forth that encompass this region is often referred to as the local group. And this is what I really mean when I say the local environment, and really testing and understanding kind of things about the very first stars or the early universe by this particular local environment. This is what I mean. And the Milky Way and its local environment is a great laboratory for kind of this type of science, in part because it's one of the only systems where we can obtain detailed 6D phase space, but also chemistry information for many, many, many individual stars using Gaia, large spectroscopic surveys. JWST is, of course, pushing us out to M31, which is why I've included that. And the detailed chemical fingerprint of the stars and stellar populations in the Milky Way and the local group is partly, and I say partly intentionally here, relatively time invariant. And so this is what enables us to do stellar archaeology. And you can see slide 3 of Alex's talk this morning to really kind of get a little bit more of an example of why stellar archaeology works. But essentially, this slide is here to kind of illustrate the fact that the Milky Way and its local environment really is an excellent laboratory. It's the near field laboratory, so to speak, of the far field. And so that's why I think there's a lot of connections here, particularly the near and far connection that I'll be speaking about today. And the near far connections between the Milky Way and Milky Way-like galaxy analogs and their earlier descendants at early times. I'm really going to focus on 3 particular examples and cases of those. One is using the Milky Way and its local environment as kind of a local laboratory for studying accretion history and galaxy buildup examples, and how we can understand galaxy formation and assembly using the Milky Way. I'll talk then on second about kind of how we can use the oldest local stars, and local again being in that local environment, to tell us about the earliest stars, the population 3, first generation of stars. And then I'll wrap up with a very short example of how I think local near field dwarf galaxies and ultra-faint dwarf galaxies, and particularly their chemical fingerprints, will tell us about chemical enrichment at early times, and the stellar populations that may be evolving at earlier times. So we'll start here with the accretion history of the galaxy. So if we go back and we look at simulations, this is just a simple simulation from the latte simulation of M12M from Andrew Wetzel and others and collaborators. You can see this is the stars of the latte simulation at starting at very high redshift, very high being 12, I suppose, and kind of moving forward, stepping to today. You can see this kind of picture of galaxy evolution where these small proto-galaxies form and then accrete into larger and larger systems, Milky Way-like systems. And as the simulation kind of continues forward, the galaxies become not only more complex chemodynamically, but also you can see all kinds of really interesting and beautiful substructure in the exterior halos of this simulated galaxy. And so if you really want to learn this simulation already illustrates if you really want to learn about the accretion history of galaxies like the Milky Way, you can actually study the halo regions of those galaxies and look for these beautiful arcs and streams and rings and so forth that are essentially the grave site of all of the structure and all of the substructure that essentially fell in terms of building up the Milky Way or Milky Way-like systems. And so some of the questions that come out of this are how typical is the Milky Way accretion history, which we can actually back out locally. How typical is it of other galaxies, of other Milky Way-like galaxies, like say, for example, M31, and JWST is in a position to answer questions like this. And JWST is also showing us how the earliest properties of stars in early galaxies, kind of early building blocks of Milky Way-like galaxies, what those look like. And so I point you to an earlier talk on the review of integrated properties of really early systems from JWST, because these will essentially be the building blocks of today's Milky Way-like systems. And I'm also interested in how do we learn about the Milky Way and the local group galaxies, their accretion and assembly history, and how do we take those assembly histories and back out how galaxies more generally form. So if you want to study the accretion history of the Milky Way and the local group galaxies, the way we tend to do this is through chemodynamics of its stars. And so this is an early example from Neeson 2010, which shows if you just study the chemical properties of stars in the stellar halo, you'll find that there are two very distinct chemical patterns of stars seen in the stellar halo. So what you're seeing here on the top panel is the magnesium over iron ratio of stars in the stellar halo. Red is a sample of stars that are in the halo but have relatively low magnesium over iron abundances, low alpha over iron. And the blue are halo stars that have relatively high magnesium over iron. And so this was found, I think, even earlier by some earlier studies, but this study is oftentimes pointed to in the literature as being one of the first to really point out that the stellar halo has these really distinct chemical features, chemically distinct groups, a low alpha group and a high alpha group. And when people then went and looked at the kinematics, this of course is still pre-Gaia, and Schuster et al. 2012, same symbols are used as before. The kind of the blue symbols are the in situ halo, the high alpha halo, and red symbols are the low alpha, or often referred to as accreted halo. You can see that dynamically, which they are quite different. So this is eccentricity of the stars as a function of the maximum radial extent that the orbit actually gets to, and you can see that the red symbols, the so-called accreted stars, not only are eccentric, very eccentric on largely radial orbits, they also are getting very far out into the stellar halo, 30, 40, 50 kiloparsecs. And this is true whether you're talking about axisymmetric or non-axisymmetric potentials. And so this led people to believe that essentially this low alpha material is likely from accreted material. And so these earlier works really said that the accreted population, there's an accreted population of stars that dominates the outer halo. That accreted population has a different chemical signature, particularly low alpha abundance, compared to the so-called in situ halo. Then there's a large amount of debates that happened in the literature from the kind of early 2000s until about 2018 as to whether or not this was one accreted system or many accreted systems. I think many groups fell into this is many accreted systems that built up the Milky Way, and so these red symbols are just essentially many accretion events that happened. And then Gaia, of course, came along, and we had different papers that have come out. Vasily Belukharov wrote a nice paper, basically looking at the chemodynamics of stars in the stellar and the kind of the metal poor stars in the stellar halo and disk. And if you just look at this top panel here, this is the phi or V theta, so it's the rotational velocity as a function of the radial velocity of the stars in the galactic rest frame. If you look at the metal poor stars, and this is decreasing in metallicity, so this is kind of like, in Alex's terms, essentially metal rich, although we still call them metal poor. And this is the kind of as you start to get more metal poor, you can see that the dynamics of the stars completely change. So in this interior piece where you have in the plane of the Milky Way, and the stars are somewhat metal rich, not really that metal rich. You see this population of stars that have almost no radial motion, but a lot of rotational motion, and that's essentially the old pre-existing disk, the old thick disk of the galaxy. Sometimes referred to as the metal weak thick disk, sometimes referred to as the aurora. It kind of depends a little bit on who you talk to. I think the field is going through a stage where people are constantly naming and renaming things, which is a little bit frustrating because it's hard to keep track of all of the names that we're using for these things. But essentially, this is kind of the old disk. But then what they also found was this long elongated radial structure that in this particular paper they referred to as the sausage, not a particularly great name. But the Gaia sausage is what it was referred to in this particular paper, which is these stars that are metal poor, but that are on these very, very radial orbits. And you can see as you go to lower and lower metallicities, not only does the disk component completely go away, the radial component basically becomes spherical in nature. And so you see a complete change in the dynamics of the stars. This is what led Vasily Belukharov in this particular paper to suggest, well, maybe this particular structure is a single or a structure that was on a particular orbit that fell into the Milky Way, which led to the idea of the Gaia sausage. Around the same time, Amina Helmi's group also looked in different orbital spaces, particular angular momentum and energy, and found that there was a group of stars, there was an overdensity of stars in this particular orbital space on the top panel. And if you look at their chemistry is they're essentially all of the low alpha stars, low alpha, low metallicity stars. This very reminiscent of the Neeson et al. 2010 result. And so this led them to believe that actually they're looking at a single galaxy that fell into the Milky Way that they called the Gaia Enceladus. Again, it depends a little bit on which literature you read. Some people call it Gaia sausage, some people call it Gaia Enceladus, some people call it Gaia Enceladus sausage. I'll just refer to it as GES here. We call it the blob. But there's a lot of names going around for it. But essentially, it is, I think the literature is converging at this idea that there is one relatively large LMC-like structure that the Milky Way likely accreted of order 8 to 10 gigayears ago, that kind of restructured the way the Milky Way actually looks. So this is an example of how you can use chemistry and kinematics to really pull apart and understand and learn about the accretion history of the Milky Way. You can also do this in detailed elemental abundance space. So we've actually looked very heavily at using magnesium and aluminum as tracers of the accreted halos. You can actually see three distinct blobs. If this is actually done with apogee data, you can see three distinct blobs: the high alpha thick disk, the low alpha thin disk, and this accreted halo of Gaia Enceladus stars. And the reason why this works in other elemental spaces, like, for example, aluminum, this is some nice work done by Danny Horta in 2021, which shows, if you just start out a galaxy and you try to do a chemical evolution model of a dwarf galaxy-like system and then a higher mass Milky Way-like mass system, this is the chemical evolution track of those systems after 0.5 gigayears, 1 gigayear, and 5 gigayears for the dwarf galaxy model, and 0.1 gigayear, 1 gigayear, and 5 gigayears for the Milky Way-like model. You can see that the aluminum does not build up very quickly in the low mass system, and the aluminum builds up very quickly in the high mass system. And so you can actually track not only what galaxy is accreting, but you can actually determine the mass of the galaxy that's being accreted onto a system like the Milky Way using these chemical tracers. So this is great because it not only allows you to pull apart the accretion history of a galaxy like the Milky Way, it also allows you to learn at least a little bit about what building blocks actually fell in. So this gives us some hope, at least in the local group, of piecing together the accretion history of the local group, and then trying to relate it back to the far field the far field galaxy progenitors that we're seeing in with JWST. And so that's one of the I think beautiful examples of kind of the near far connection, where you can pull apart the accretion history in the near field using these detailed chemical and dynamical tracers, and then compare the properties of those building blocks that we see today to the properties of the building blocks we see in the far field with JWST. Now, the accretion of galaxies onto Milky Way-like systems also completely can change the system itself. It can create all kinds of things, like it can also create a bimodal alpha metallicity distribution in the galactic disk. And so this is the so-called tube infall. This is just one example of how the accretion of a system onto a Milky Way-like system can actually lead to a bimodal distribution in the alpha metallicity distribution in the galactic disk, where you start with a proto-galaxy here. This is a cartoon from Capini, Christina Capini's work, where you basically take a proto-galaxy and then you allow gas to flow into that galaxy, forming stars in the early galaxy, and then you basically take proto-galaxies that are gas-rich. They infall for a second time, so you have the second infall, which is somewhere down here, of more gas onto that galaxy, which can then lead to a bimodal distribution in the alpha metallicity diagram. And we actually see bimodal distributions in the Milky Way, at least, and we're actually trying to figure out if there are bimodal distributions outside the Milky Way as well. So this is an example of the alpha metallicity distribution in the Milky Way in kind of the background Hess diagram. The lines represent a two infall model, which is kind of in the cartoon is depicted on the left side. Each point is represented by a particular time in that model. And so essentially it proceeds as the following. The protogalaxy begins to collapse and form stars. And as it accretes more and more gas, it forms stars. And as chemical evolution proceeds, the alpha metallicity, or the alpha decreases as you get more and more type 1a supernova, and you get more iron, essentially. So the alpha to iron ratio decreases. And then at about 9.4 gigayears in this particular model, you have a second infall. That could be an infall of, say, a Gaia Enceladus-like system that infalls and brings a lot of pristine gas into the system. And that pristine gas then decreases the metallicity and slightly increases the alpha abundances. That's why it goes from this to over here. And then as that gas settles down and begins to form new stars, you continue to proceed down this particular track. So this leads to this bimodal distribution in alpha metallicity. There are other models, of course, that can produce this bimodal distribution in alpha that we see in the Milky Way, things like clumpy star formation. There's some beautiful work done by Victor De Battista and Clark et al., 2019, which kind of go into this. And we actually see very clumpy star formation going on in JWST images. And I put some of the references down here for that. But this is just one example of how accretion can actually induce different chemical patterns that we can see in Milky Way-like systems and in the local group. This particular two infall model does require a particular event to occur. That's that second infall, that dwarf galaxy-like or LMC-like system, or in our case, it potentially would be a Gaia Enceladus-like system falling into the Milky Way that can produce that alpha bimodality. So it may not be a generic feature in galaxies, but it is a feature in our Milky Way. And so there was a large conversation about pushing this out, pushing galactic archaeology out to the local group beyond the Milky Way into, say, M31, and asking, does this bimodal feature exist in M31? Because if it does, then it might imply, this type of two infall model in M31. And if it doesn't, maybe then it doesn't imply that M31 has a two infall model. So this is what we see in the Milky Way disk. Where we actually see this beautiful bimodal distribution in the alpha metallicity diagram. Recent results from JWST, individual stars in M31's disk with JWST from Niederber et al. Shows no such alpha bimodality. This is still, as far as I know, preliminary. I've only been able to find a conference proceeding on this. I haven't been able to find a refereed article yet. But there has been some work done on planetary nebula in the disk of M31, which actually do show a alpha bimodality. So this is from Chaki Kobayashi's great 2023 paper in red squares showing the abundances of planetary nebula and emission lines, and overlaid are their chemical evolution models showing this beautiful alpha bimodality. So it appears that there's a little bit of a discrepancy in the literature right now as to whether or not there's an alpha bimodality in the disk of M31. I think it's still unclear, but it's an area that I think will be really exciting with JWST to really learn about the accretion history of another system like M31. Okay, so moving along, the second thing I wanted to focus on is looking at the oldest local stars as analogs or as tracers, so to speak, of the population 3 stars. And so let's say you're interested in what JWST can learn about the nature of the first stars. I put this here in part because this is one of the key questions of this conference. So I hope everybody's interested in this particular question. And the way I see it, you can answer this question in a couple of ways. If you want to know about the nature of the first stars, you can try to observe them at high redshift via JWST. And this is direct detection. And we had a talk this morning. I think Raphael spoke this morning a little bit about this. Or you can observe low mass stars in the local neighborhood that have only been polluted by the first stars or are themselves population 3 stars. And Alex G had a nice talk about this. There are ongoing searches for the first stars in the high redshift, but I would argue that probably one of the best paths forward in trying to understand the nature of the first stars is observing the local the oldest local stars that you have access to and looking at the chemical nature of those oldest stars to get a kind of indirect understanding of the nature of the very first stars. And so in order to do this, you need to first find the oldest stars and in the local field. And so if you look at the Milky Way's earlier simulation work in 2010 by Tomlinson, if you just try to look at what is the fraction of extremely metal poor stars which were born, so to speak, before redshift 15, if you overlay that with the Milky Way, you find that most of the oldest stars that are both metal poor and extremely, extremely old, by fraction are really found here in the central regions of the Milky Way. And Alex kind of spoke to this earlier this morning, which is great at some level because that means that the oldest stars, at least potential second generation stars after population 3, should be in the central region of the galaxy. The downside to that is if you look at the metallicity distribution in the galactic center from Apogee, from many works, it's actually significantly metal rich. We're not talking like metallicities of -3 or -4, which is really where you want to be. We're talking metallicity 0, iron metallicity 0. And so it's extremely challenging to actually find very metal poor stars in the galactic center and the oldest stars in the galactic center because you're just completely swamped by the sheer volume of very metal rich stars in the galactic center. And so this was kind of even borne out in more recent work by Karim El-Badri. If you just look at the number of giant stars that formed before Z of 5 in different simulations, in the fire simulations, and you look at the radius of the radial distribution of those stars, they're really peaked towards the inner galaxy. So most old stars are in the inner galaxy. If you look at the fraction of stars that were born of that population that was born before Z of 5, there actually peaks in the outer galaxy in the halo region. And that makes sense because the halo is dominated by old metal poor stars, whereas the interiors are dominated by kind of oldish metal rich stars. And so it's much harder to find. That said, if you look at the fraction of stars that are more metal poor than -2 that are born before metallicity -5 in most sims in the fire simulations, by fraction there are more metal poor stars in the inner galaxy that were formed before Z of 5. And so this really motivates the idea to go to the inner galaxy to find the most metal poor stars, more metal poor than -2, because these will be truly, truly old. So this is what many surveys have done. This is just a smattering of some of the surveys of metal poor stars. This is what prompted people to go and search for metal poor stars in the galactic center. So the Ombolus survey, the Combe survey that we did here in Texas, and the PIG survey being done with the Pristine survey. We have found now tens or hundreds of metal poor stars in the galactic center that are both old and extremely metal poor. And of course, Gaia has really enabled us to do this even better with this, particularly with XP, with photometry, the spectrophotometry. So this is just a showing of the number density of stars in the galactic center above metallicity of -0.4 and below -1.5. So you can start to see them peaking in the galactic center. Pre-Gaia XP, you can do this with photometry. Embla, Combs, and Pigs are all great examples of that. And also large spectroscopic and both optical and infrared surveys. And I've put some of the references there. But now XP Spectra are giving us a way of doing this without the need to go to photometry. Some of these surveys have produced some really interesting results regarding the nature of the first stars based on looking at the abundances of these very metal poor stars in the galactic center. Things like there's evidence for top-heavy IMF, and this is just by looking at the plateau of the alpha abundances in the metal poor stars. They plateau at very, very high alpha abundances, which would be suggestive of a top-heavy IMF. There's also evidence for globular cluster disintegration. So if you look at the magnesium aluminum plane, there is a group of stars that are both metal poor and old in the interior parts of the galaxy that have very, very high aluminum that we just don't really see outside of globular clusters. So it says that some of those stars may be coming from very ancient globular clusters that have disintegrated and are now in the galactic in the central region of the bulge. This is also you have the ability with these metal poor stars to look for pair instability supernova signatures. And there'll be talks by Stefania and Alex on this particular topic. We haven't really found any, as Alex kind of mentioned, but these samples represent the ability to potentially look for them. And I think Alex already covered this in detail. We're also really interested in carbon-enhanced metal poor stars. So these are metal poor stars that are also carbon-enhanced by a factor of +1 in carbon. 80% or more of these stars at very low metallicity are carbon-enhanced. And they come in different flavors. The carbon-enhanced stars can come in a flavor that is enriched in S process, so the CEMP-S, and not enriched in S process CEMP-No. It's believed that the CEMP-S stars are likely mass transfer, and the CEMP-No stars are likely potentially true population 2 stars, so single stars, although not all of them are, single stars that may have been actually second generation after the first generation of stars. These surveys of the most metal poor stars in the galactic center have found that and I'll just quickly fly through this just to say that the fraction of CEMP stars in the galactic center for metal poor stars seems to be significantly lower than in other regions of the galaxy, in the halo and in dwarf galaxies. And so this is something that we're trying to figure out now why that is the case. But the CEMP fraction is changing depending on where you are, and that has some implications for what could actually generate and create these CEMP stars. Looking at the time, I'm running out of time, so I'll just quickly mention the last topic that I wanted to just simply flash up and say, which is that I think in terms of near-far connections, I think the near-field ultra-faint dwarf galaxies represent a wonderful ground, really to look at the descendants of population 3 stars. And so this is an example, a very recent example from Rossi et al. 2024, who shows that if you look at the very local ultra-faint dwarf galaxies, Bootes 1, you actually can find stars that have signatures that where they have only really been polluted by potentially population 3 stars. These are population 3 descendants. And since UFDs, these ultra-faint dwarf galaxies, are extremely low mass, they really are allowing us to sample and probe the less massive more energetic population 3 supernova explosions. And so this illustrates, I think, the value of looking at local UFDs to probe the nature of the very first stars. And I think we need to either have a survey, a more comprehensive survey of these ultra-faint dwarf galaxies in the near term to really look at their metallicity distribution functions to see if they're metal-free, and if you can find any metal-free stars, and to look at the CEMP fractions of these ultra-faint dwarf galaxies. And we're starting a survey with the Hobby Everly telescope here in Texas, but I think there's also potential to do it with JWST and other surveys as well. So with that, I'll leave up my conclusions, or my summary, and take any questions, and hopefully this opens up some discussion.
Okay, so the talk is open for questions. We're particularly going to encourage questions from people that haven't asked questions yet and younger folks in the audience. Everyone in the back that thinks they're hiding.
Hi, Keith. This is Alex. Thanks for a wonderful talk. I'm wondering about the alpha plateaus in the center of the galaxy compared to elsewhere. Is it not possible to attribute this to differences in the overall star formation efficiency, or do you really think that this is like, given uncertainties in yields, or do you think this is really very clearly IMF variation? If that makes sense.
Yeah, that does make sense, and that's a great question. I think it could be related to star formation efficiency. One of the things that we need to do in more detail is actually do detailed modeling, chemical evolution modeling of this particular region, and just see whether or not the star formation efficiency, you can crank them up enough to actually get this particular result. This is the Combs result, although I think there's now more evidence from the PIG survey and other surveys that there are these relatively high plateaus in the alpha abundances within the galactic center, which could, I think, be indicative of top heavy IMF. So I would say that the top heavy IMF is one potential result. It is also true that star formation efficiency could be the answer as well. I think we need not only a little bit more data to say so more conclusively, and also chemical evolution modeling should be able to help as well.
Yes, Rachel.
I qualify for neither of the categories you mentioned, but I do have a question. Keith, this is Rachel. Thank you so much for that beautiful talk. Can you expand a little bit more on, I think it was your second bullet in your conclusions, about how JWST and possibly even other facilities, like maybe in the future, ELTs or Roman or whatever you want to talk about, can extend these studies out to larger distances and further into the local group?
Absolutely. So I think when we talk about doing galactic archaeology or learning about, say, the accretion history of the Milky Way is just one system, of course. It's one realization. And what we really want to do is learn about the diversity of accretion histories outside of the Milky Way in the local group to really understand, and their building blocks, to understand what the diversity of the building blocks may have looked like at the earliest times. And so JWST is already starting to help do this by looking at the accretion history of structures like M31. We could do this in M31's disk now with JWST, but also it should be possible to look into the deep regions of M31's halo to really, and get detailed chemistry of the individual stars there to really start to understand its accretion history. And Fangs and other surveys have started to do this in M31 as well. But with other, not only JWST, but with Roman and Ruben, Ruben will give us kind of the very high sensitivity we need to do very low surface brightness structures in the local group and beyond, of course. And with follow-up spectroscopy in future missions, JWST included, you actually should be able to start to look at doing detailed abundances of individual substructures in these low surface brightness features to really get a handle on the diversity of the protogalaxies that kind of built up the local group. So that's probably what I would say in regards to that. I would say one other thing, which is that I think that what JWST and other surveys looking at doing a more comprehensive study of the ultra-faint dwarf galaxies, although I kind of swept this under the rug or flew by it rather, I think will be really important because we actually need to look at these ultra-faint dwarf galaxy systems to really understand the chemical distributions, to understand how they were built. And since they are probes of the early universe or probes of the first stars potentially, looking for metal-free stars, as Alex kind of mentioned and pointed out in his talk, in these ultra-faint dwarf galaxies is a real challenge. And so I think that future missions and JWST could also really help out in that regard as well.
Thank you.
So we have a question online from Stefania Salvadori. While she asks her question, I'm going to ask if Grace can come ahead up.
Yes, thank you. Okay, so I have a related question to the one of Alex G. so of this alpha plateau. So can also be this due to the fact that the progenitors of the galactic bulge are more massive than, for example, ultra-faint dwarf galaxies, and so they can retain more of the metals produced by more massive stars.
Yeah, that's also possible. It would be so at these metallicities, I would expect that the more massive let's see. Sorry, at these metallicities, I guess I would say that if these were built from very massive progenitors that have fallen into the bulge, one might expect their alpha abundances to still be relatively high, which is what they are. So it does go in that direction. I do think that, and similar to the answer to Alex's question, I think that we need to do better chemical evolution modeling of the inner galaxies metal poor stars to really get a handle on exactly what's causing the plateau to be so high, whether it's star formation efficiency, whether it's the IMF is top heavy, or whether it's, for example, that the progenitors of these particular stars that are at the high plateau were just from extremely massive systems that have fallen in to create the galactic bulge. Very good question.
All right, let's thank Keith again for an excellent talk.